Thank you. Thank you for the presentation and the opportunity to talk in this workshop. I am going to present results on the constraints. This is a joint work with Tikan and Vigan in Paris. We have introduced something we call the seed to solution method in order to construct solutions to the constraints satisfying certain asymptotic properties. And another topic I would like to overview, and hopefully this will not be too technical, I will try at least. The second topic will be about the stability of massive scalar fields, Klein-Gordon fields. This is a work with Yuma, and we have introduced a technique called the Euclidean hyperboloidal method to tackle this problem of stability near Minkowski space. That's the classical result in the field. And the third topic is actually very connected to, partly connected with the lectures of Hans, where we also produce the parametrization of data. We call them singularity data on gravitational singularities. But then we move on to a completely different issue, which is the question of crossing singularities and defining certain bouncing. And this is a joint work with Bruno LeFloch, he's in Paris, and Gabriele Veneziano in Geneva. So let me first show you some results concerning the constraints. So everybody knows about the constraints, and what my point of view would be to fix matter fields, which I call H star, denoted by H star and M star, and to look for a solution to the constraints where H star and M star are the mass and momentum as sources in the constraints. And I want to find the metric and second fundamental forms satisfying the equations. And this will be done in a situation where the manifold is asymptotically flat. So all the issue is about the decay at infinity, at space-like infinity. And in the second part, in the second topic, you will see that these sort of results are useful or used in order to look at the evolution in the next step. But at this moment, we only look at the constraints. I use the notation G curl G for the Einstein operator. And I remind you that there are many people, including in this audience, who worked on the constraints and proving, constructing various classes of solutions on compact manifolds, or most of the work is done in a vacuum. And the work, as you know, started with Lichnerovich in the 60s. So there are many, many names. I put some of them, probably I may have forgotten some names. And my interest here was for a more recent work by Carlotto and Rick Schoen, as I'm going to explain. So this is our point of view. We pick up something we call a seed data, and a seed data should be considered as an approximate solution to the constraints. And to pick up such an object, a metric and a second fundamental form, is for me a way to introduce behavior at infinity. I want it to be prescribed. And then I'm going to discuss the solution to behavior depending whether you have strong conditions of decay or weak conditions of decay. I want to produce a solution, but also to control the discrepancy between the ansatz and the actual solution that you will construct. So beyond the fact that having a lot of solutions is something of interest, especially in the asymptotically flat case where there are not so much work done yet. My motivation came from this work by Carlotto and Schoen, who solved a problem called the localization problem. And some of you, or maybe many of you, know about it, but I will remind you what it means in a few minutes. They were looking at the vacuum case and basically imposing at infinity a certain behavior Schwarzschild or Minkowski at a certain rate of decay. But from their work, there was a question whether you could do this kind of localization at the sharp 1/r rate of decay. And this was unknown at the time of their work. And so this is a problem that I wanted to consider in collaboration with Tika and Wigan I mentioned earlier. So how do we produce solutions that have low decay? So I'm not specifically interested in here first at a decay like 1/r, but even a much lower decay is also of interest. And to produce a lot of such solutions by extending the techniques of Carl Otto Schoen, I end up looking at critical elliptic estimates and getting this notion of mass correctors, which I think is quite interesting. So the picture you see here represents the class of solutions that we have constructed. Okay, I will return to it, of course, in a few seconds. Now, let me say that more recently, there have been a very nice work by Aretakis, Sismek, and Igor Onionsky, revisiting this question of gluing and localization, and in fact solving exactly the conjecture that was proposed by Carl Otto and Schoen a couple of years ago. So let me present the sort of results we have. So we have actually, depending on the decay condition that we put, we have different solutions. So here I'm going to pick up two results. The first one, and in fact it will be as a vacuum here because that's just easier to present. So this is what we do here. You give me a G1 H1, a metric, and a two tensor, satisfying certain decay condition at infinity. And I use the exponent P sub G for geometry or P sub M for matter in order to represent the decay properties of G1 and H1. Okay, or the operator. When you plug them into the Einstein operator, you get certain decay. And this is how I define PM. Of course, we do that with certain norms. So this is definitely not the full result. And you can look at the paper if you want to see the functional spaces that need to be used. So basically what we do is that we extend the technique, the method of fixed points that Carl Otto and Schoen had proposed. And by doing so, we form an ansatz, an approximate solution, we produce an actual solution. And then comes the question of how you compare in terms of decay, in terms of norms, the difference between G1 and G or H1 and H. So the answer to that last question depends on how accurate your Riemann, your Einstein approximate solution is. Meaning that if PM is quite small, less than 1, you have the statement that I wrote here, that is G and G1 somehow agree to the rates that you would have expected. If PM is 1, you have a result that is a little bit different. And the third case would be PM is very large. So for the last two cases, you have certain integrability condition that you need on the Hamiltonian or the momentum to be in L1, but that's not essential. What is more interesting is that there is a mass term that we call a mass corrector that comes from iterating the map, the fixed point map that you use behind the proof of this theorem, and which you can also use in order to define a numerical algorithm. So there is really this idea that you give me an approximate solution, I do certain iterations, I produce an exact solution, and then the question is comparing the two, the initial data and the final solution. And this is given by the statements in this theorem. There is an additional mass corrector, but this mass corrector is something you might have expected because it's a contribution to the idiom mass. It's spherically symmetric. It only depends on a scalar parameter. And this scalar parameter, m tilde, I can also compute it from the data, at least to a certain order. So basically, this mass correction is the integral of the Hamiltonian applied to your data. Okay, so all of that is quite natural. And so let me skip this page, is simply to explain what you get if you take the various limits of the exponent going to 1/2 or going to 1. And that's basically what I told you by discussing the theorem. So let me say that for the proof, what we do is, maybe I will not give you too many details about that, but basically we follow the general scheme of Carlotto and Schoen, looking at the linearized Hamiltonian, linearized momentum, the adjoint operators associated to that. So they have different orders, different systems. They are scalar valued or vector valued. There's first order, second order. So there is a combination of all these operators that produce a nice, or maybe not so nice, nonlinear elliptic system. And this is a system that you have to study. And we follow, actually, an important idea goes back to Corvino and Schoen, maybe already 10 years ago, something like that, who introduced the variational framework to handle this coupled system. So the solution will appear as the Euler-Lagrange minimizer associated with this formulation. And then comes the functional spaces. So for us, it's important for us to work in weighted spaces that takes into account the decay at infinity carefully. And in addition, to work with Poincaré cone inequality and elliptic regularity at the harmonic level of decay. So this is basically the new aspect of that. And I think this is not a place to give you more details about the proof. So what I'm going to do next is to show you the connection with the work of Carlotto-Schoen that we have done. And this was somehow our initial motivation. So to solve this localization problem at an optimal level, this is a problem that they proposed. I guess if I show you the picture below, it's going to be more clear. So what you do here is that you decompose space-like infinity into 3 regions. There is a big angular region where you are going to decide that your solution to the constraint is your metric is the Euclidean metric. There is an also big angular region where you pick up the Schwarzschild metric, for instance, but you can do more complicated construction. And for instance, Piotr Kruchiel has done a lot in this direction. But so here I'm taking Euclidean in one direction and Schwarzschild in another direction. And then there is the interior of 2 cones, I mean, the region contained in between 2 cones. And in between, what Carlotto and Schoen do is that they solve the constraint in this region. Outside, just trivial. So they can solve in this narrow region. And what they obtain was a solution with a decay 1/r to the power p, where p was between 1/2 and 1. So they could take it to be as close as 1 as they want, but they could not take it to be 1. Their proof did not give any such result. And so this is a question that they propose. Can we construct solutions where the gluing between the two would be at the 1/r level? So my answer to that with Tika and Huygen is to actually slightly relax the localization condition. So what we look for now is a solution that is asymptotic to the prescribed metrics, Schwarzschild or Minkowski, at a certain supercritical rate. So we could basically impose any rates we want, but not the exact solution in these directions. And in the narrow angular region that remains, we do achieve the 1/r decays that Carlotto and Schoen ask for. So this is a result. You have the vacuum Einstein equations on a manifold, say with a single asymptotic end. We decompose the asymptotic infinity into 3 asymptotic angular regions. So they depend on some angle, A plus epsilon, and a small, I mean, the complement of something slightly bigger, and then the narrow region, the transition region, which I have denoted by TA epsilon. So if we again pick up the Euclidean metric, the Schwarzschild metric, and we do this sort of gluing, except that for us, this is not gluing. What we do is that we solve globally in the whole space, on the whole manifold. So that's a big difference compared to all the works that had been done on gluing. It's really a very different philosophy, but this is the result. So we have a huge region where our metric is the Euclidean metric plus 1 over r to the power q. So it's really super critical, 1 over rq, q strictly bigger than 1. We have another region where we can pick up the Schwarzschild metric, also with a high decay. And then we have the connection between the two, this narrow region, where we do achieve 1 over r decay, and we can also say something about the form of this 1 over r coefficient along the lines of what I told you in the first theorem. So the element of proof here is to further refine our C2 solution method to design certain seed data with parameters. Maybe I just show you very briefly the next page. So you see that I'm going now to pick up a G1 depending on certain parameters. So I have a real parameter S, T are real parameters. I have certain fields that I pick up at a sphere at infinity. I call them psi and phi. And then I'm going to adjust them. If I pick up randomly, I mean, in any way, I do produce a solution. And then all the game will be to pick these fields and these parameters in such a way that I do achieve, so if I show you the page before, I do achieve the condition in this second theorem. So as I told you before, there is a beautiful work now, which is fully geometric. Of course, our paper is 50 pages, and it's more like a PDE paper, and their work is a fully geometric 200-something pages. So just a different way to attack the same problem, but they do answer the problem raised by Carlo Toschen positively, and they also look at other sort of gluing, characteristic gluing, not only space-like gluing. So for me, this kind of result was important because of the other topic I'm showing you now about the global evolution problem joined with HUMA. Are there any questions on this first part?
So if I may, a quick question. So you're getting you're not getting a flat metric, right, in this cone region, but perturbation which decays very fast. Exactly. So are you using weighted spaces where the decay depends upon the direction of decay that you're looking at? Is this the key of the technique, or? Maybe it's too complicated, then just forget my question. Just to get a very quick idea of the technique.
Yeah, but I mean, the weights are not direction dependent.
Okay, good. So that was my question, whether the weights are direction dependent. Okay, thanks.
Okay. So let me skip the details about how to feed that, and I now move to the evolution. So basically, I'm taking now some of these data, and I want to evolve them, and I evolve them in a situation where I have a coupling with a Klein-Gordon field. Of course, this problem is something that I work on for a number of years, and some other people also have contributed, which I'm going to mention. But what I want to show you today is somehow a version of our main result, which somehow we simplify, because if you see what was done already for the constraint, it involves a lot of rates, of exponent, of rate, etc. So basically, my goal for this section here is to extract one result, which we feel is somehow the typical results that is produced by our technique of the Euclidean hyperboloidal foliation method. So these are just the equations. Either you think of Einstein coupled to Klein-Gordon, or you think of f of r modified gravity, but you do the classical transformation and you end up with basically the same system. So beyond the initial results by Christoph Dulu, Kleinerman, Lydia Biery, Zipster, Hans Lindblad, Igor Niensky. So in a vacuum, so all these works, as we know, were in a vacuum. So it's only more recently that people have looked at the coupling with matter, especially massive matter. If the matter is massless, that's relatively easy compared to the vacuum case. But in the massive case, you need a lot of modification, extensions of the techniques. So this was done first in a situation where the outside of a compact region were Schwarzschild initially. And then it was done by Alex Ionescu, Benoit Possader, and Yuma and myself by two different techniques for general exterior. So basically that's what I would like to show you today, just to extract one result, which I think is more typical. And since then, and also in parallel, there have been a lot of work, especially by participants or speakers of this conference, about other matter field, Vlasov matter, Maxwell. So I noticed that Hans Lindblad, for instance, will be talking about the coupling with Maxwell and Klein-Gordon in a few days. So we certainly look forward to his talk. And there have been contributions by the organizers of this workshop as well. So myself, I developed this idea of Euclidean hyperboloidal foliation method already a few years ago, with the idea that if you want to properly capture the decay in time in the interior of a light cone, it's better to use hyperboloids. And if you want to to correctly capture the decay in space, you should use asymptotically Euclidean slices. So with Yuma, we merge these two kind of foliations, and we develop a method to tackle coupled system of wave and Klein-Gordon equations. And in fact, as I may show you a little bit later, we really have this in mind, that this should be a tool that can be used for other systems that couple nonlinear wave equations, Klein-Gordon equations, and we try to present our work in a way that it's easy to see where the general arguments and where are the arguments that are specific to the Einstein equations. So I'm not going to enter into any technical details. So let me move to the actual statement that I want to show you. Okay, so I'm going to show you one theorem, which is essentially a theorem that also is given by Ionescu and Possader. So the way we think of this problem is with the idea of a reference spacetime. So it's really the same idea as the seed metric that I introduced for the constraints. So we consider metrics that we define as the decomposition of the Minkowski metric plus H star, defined on just R3 or R1 plus 3, Lorentzian signature. And what we write the expression of the Ricci curvature in wave coordinates, basically. Okay, so we somehow remove the effect of contracted Christoffel symbols. And then we look at two regions, the exterior of a certain light cone and the interior. We define weighted norms. So maybe here you will see a little bit more about the functional framework similar to the ones that we have been using before. So here there is a norm. The Japanese bracket R plus T is put to a certain power lambda. And we use translation, the boost, and the rotation in order to define our norm. So this is a subnorm. We also use an energy norm in a minute. But at this level, to describe the amplitude of the reference spacetime, we formulate it in subnorm. And we have three conditions. The first condition is about the fact that the metric should be asymptotically flat in a suitable sense. So basically, lambda is a rate of decay of the metric. So it's between 1/2 and 1, because it goes from the ADM, finite ADM mass on one end to the Schwarzschild behavior on the other end. So everything has been rescaled. So what I'm saying corresponds to the meaning of these norms. And then there are two more conditions about the Ricci curvature. Okay, and before I basically did that, I told you before that I plug my ansatz into the Einstein constraint operator. So here what I look at just the vacuum. I'm looking here for this part at the vacuum Einstein equation in space-time now. So I look at this Ricci curvature, and I want to impose a certain decay at infinity and smallness at infinity. So this is done through three parameters. Lambda is a rate of decay, epsilon star is the size of my globally my solution, and capital N is the number of derivatives that I allow, and this capital N will be typically 20 if you are interested in my result. Now, if I have such a reference, yes, certainly.
Yes, so your norms are space-time integrals, or these are Sobolev norms in space, or on hyperboloids? What are the norms?
These are no, I mean, these are subnorm. So there's not subnorm.
So that's over space
and time.
Or over a surface.
Say it again.
Is it over the space-time, or is it over a hypersurface?
No, it's over space-time. It's over space-time.
Thanks.
So given such a metric, I define, then I take the trace of that, right? So I have my reference metric, which is defined in space-time. It's small in subnorm, like stated. And then I take the initial trace of that to have the notion of lambda and epsilon admissible initial reference metric, if you like, metric and second fundamental form. So I take this object, and this is the object that I will use now to formulate my initial data. So you will see that it's just going to take two or three slides to be stated. Now, I have a second condition that comes now, which we call light bending property. So maybe a better terminology, but this is the best we could find. And what we simply do is that we look at one component, the incoming null component of our reference metric. We multiply it by R. So R, we have global coordinates. R is just the usual distance. And we require that this quantity RG star is basically is bounded below. And this is something that we only impose near the light cone domain, which is a certain region. I mean, a certain region near the light cone, defined as you see on the screen. So the reason for that, first of all, I should say that it's not really necessary to get the stability and to get the result. But all the game I'm playing here is to somehow I want a theorem that is neat and somehow easy to read. So we have these conditions that give you a key sign to derive energy estimates and certain pointwise estimates as well. So it makes the whole proof and the statement more transparent. So, and of course, it's very much motivated by the fact that the Schwarzschild metric with positive mass enjoys this property. So there's a picture that tries to illustrate it. So we'll impose this light bending condition on our reference metric. We have here just a little bit of calculations to say, following what Hans Lindblad, Igor Onionsky had done, we merge flat metric and the Schwarzschild metric basically around the light cone, and we produce a merging metric which satisfies all of our conditions. And especially, of course, this sign condition, if we compute R times this this coefficient, this Lycon coefficient, we basically find the mass plus something of higher order in terms of decay. Okay, so we have this reference, and this is what I'm going to use now. So we will define an initial data set. So G0, K0, there is a matter field now that comes in the picture, phi 0, phi 1, by requiring that the constraints are satisfied. We assume that there is a decomposition of this initial data into first part that is a light bending admissible initial reference, satisfying. So we have just some very, very minor decay condition that we write also on this reference. But what is really important here is a part, the perturbation. So we call it a perturbation. And this perturbation now will be finite energy. So we somehow jump from the subnorm that we use so far to now perturbing this reference controlled in subnorm by a perturbation which is now controlled in L2 norm. So of course, much, much, much weaker. So this perturbation is defined through a certain rate, K kappa. So we have a kappa, the R bracket is still the Japanese bracket square root of R squared plus 1. And we have a parameter epsilon to measure the size of our perturbation. Okay, sorry, there is a second condition, of course, the metric, second fundamental form, and the matter field. Okay. So our theorem of evolution is simply the global evolution of this object, so which I'm now going to state. We fix an integer, at least 20. We pick up an initial data with certain parameters. And the parameters are like I'm writing here. So these are really quite mild condition on the decay, and especially the matter field can decay quite slowly. And then we need a certain restriction. So this is a regime. The regime that I'm describing with this theorem is a regime where lambda is close to 1. And in this regime, we have a connection between how close lambda must be to close to 1 and how close kappa is to be close to 1/2, right? If kappa is close to 1/2, this is a worst decay, or if mu is close to 3/4, this also corresponds to a matter field that will decay very slowly. So we relate these parameters in the way that is stated, and we also relate the size of this parameter. And in fact, this is something that we have done in our proof in a very systematic way. So if you go through the proof and you look at all the steps, we were very careful to write conditions for our various parameters. So we could somehow discuss various classes of solutions. So maybe I should first finish the theorem. So the theorem says that the maximal globally hyperbolic Cauchy development of this data is future causally geodesically complete, and our solution approaches Minkowski spacetime. So this is a usual conclusion that you want when you are in a near Minkowski regime. And now let me add a few remarks. Vacuum spacetime, we recover exactly what Lindblad, Ronionsky had done. We also recover our earlier result where the initial data set were with compact support somehow, I mean, meaning Schwarzschild, exactly Schwarzschild outside a compact region. And maybe something I should say is that we really, along the lines that I'm presenting today, we have actually revisited our presentation in this work that is somehow old, but still I think useful to read, maybe for if you are interested in that. And so please send me any comment you may have on this new version. We try to be careful in including new references that we found, but please do not hesitate to send us an email. And let me maybe finish this screen. So phi has only some mild decay at infinity. So yeah, so maybe let me just summarize by saying that our method is robust, cover various metrics. But the point is that different assumptions on the reference metric will correspond to different ranges of parameters. And as I mentioned before, there is an independent proof of this result, the same result by Ionescu, Posader, except that they use quite different spaces based on Fourier-based spaces. And so it's not easy to compare. This would something that should be done, but to actually compare our spaces to the spaces that they used. Piotr, you had a question?
Yes. So here you said that when phi is 0, you recover Lindblad and Rodniansky. But so I was wondering if your initial conditions are how different they are in this case from Lindblad and Rodniansky. They're identical, or they're weaker, or how do they compare?
I think they're slightly different, but
So it's not really recovering, but you get a similar spirit or something like that.
I guess it would be more accurate to say like this. Yeah.
But you're starting from a hyperboloid, right? So you get a solution to the future. You don't get a one to the past.
No. We start from.
You start from t equals 0 from.
Yeah, we do. Yes.
Okay.
Yes. It's really the same in this sense. So yeah, maybe some rate of decay are not exactly the same, but
okay,
really virtually the same.
Okay, thank you.
Okay, so I do have maybe one more slide about this, and maybe again to make a little bit of advertisement about that. So you will see the new version probably tomorrow. I think it's not yet accessible on Archive, but by tomorrow it will be visible. And as I said before, we try to split the presentation into pieces that can be read almost independently, and most importantly can be used to tackle other problems. So all the first part has nothing to do with the Einstein equations. They look at wave and Klein-Gordon equations and produce all the tools that you need if you want to use a foliation that, as we construct, connect Euclidean slices and hyperboloidal slices. So we really connect the two. So again, to answer the question by Piotr, we do solve everything from a flat initial slice. So the tools are given here in terms of calculus rules, in terms of integral and Sobolev estimates, pointwise decay. So everything is I think nicely, as far as we could do it, put in different sections, organized in different sections. And then the part two, the second part, begins with the analysis of the actual equations. And in fact, we prove more in the second part that we actually present first in the beginning of the paper, because we felt that it was really a better way to first have in our section 2 results that are a bit easier to read and to understand, and to put some more technical parts in discussions in the second part of the paper. So we do, commutative. I mean, all of that. The titles maybe don't say very much, but the point is really the organization of that hopefully would be useful if you want to extend. For instance, maybe Hans Lindblad will be talking about Maxwell coupling, and this is something also that we had in mind, but we didn't do that. But there are many other systems I think you can think of. So do you have any questions maybe on this part? I can maybe stop before moving to the last topic. So if not, okay. So if not, maybe I use remaining time to tell you about scattering, cyclic spacetime. So this is a fascinating topic that we initiated with Bruno LeFloch and Gabriele Veneziano. And so the game here is to look at contracting, expanding spacetimes, and understand what kind of junction conditions you can impose, right? So it's easy. I mean, there are examples of course, contracting metrics, and we have seen that in the talk of Hans Ringström, for instance. And there are, of course, you change the time, you can, of course, construct solutions that expand, but now can you connect these two things? And the answer is yes, and that's not, we have plenty of people had local physicists that look at that, but very little mathematics had been done before our work. So the way we tackle that is to consider the so-called quiescent regime built on work that Hans described just today. We have the coupling with a scalar field, or it could be stiff or compressible fluid. So this is a setup that we have in mind. We know that certain local existence exists, starting from the singularity. You can solve locally and construct a space-time. So we basically do that in one direction. We do it in the other direction, I mean, towards the past or towards the future. And then the question is how you connect the data. The data are denoted, so singularity data. So we have G plus, K plus, phi plus, phi 0 plus, phi 1 plus. This would be data in the future that we are going to define from our data or our maybe solution in the past. And the object that connect both sets of data, we call it a singularity scattering map. And by using this map in order to glue solutions, we get spacetime, which we call S-cyclic spacetime, where this S stands for the map that we pick up. So the question, I mean, the point of view here is that you are not going to construct solution just from nowhere, from no physics or no idea. You need to decide how you want to make this gluing. And basically our contribution was to produce a classification by working with general spacetime rather than spacetime with symmetry, which is all the physics that was done before in this direction. People were looking at spacetime with symmetry because things can be computed somehow explicitly. So symmetry was always assumed before. And it was always also spatial junctions that people produced. You know, they say, okay, maybe we connect in this way or in this way. But this is not our point of view. Our point of view is to look at general spacetimes. This is very important, and to understand all connections, all junctions that are possible. We don't tell you which one you should choose, but we tell you how many junctions are possible. And the answer to that question is surprisingly simple in the end. There is a classification that says that there are very few degrees of freedom allowing you to pass from parameters from data in the past to data in the future. Very few parameters, and we can describe them explicitly. So in fact, in the course of this work, to answer this question, do this classification, we actually did exactly the same analysis that Hans Ringström showed us in the first part. I mean, or partly, I would say, in the first part of his lecture. So it's amazing that having in mind different questions, different problems, we end up doing the same thing. So I think I will skip that very quickly. So we have an ADM foliation. I guess I don't have so much time, but you all know about having a foliation, having the ADM formulation, and Kastner is of course our typical example. And these Fuchsian techniques have been outlined in the previous lecture. So I built on that. I'm not revisiting that and the talk of Hans Ringström was very explicit and very detailed about pushing these ideas as far as possible. So I'm not interested in. I mean, I'm interested in this question, but that's not really what. This is a very interesting topic, but I'm not doing that here. And instead, I concentrate on the asymptotic data, the constraints, and of course the junction. This is the final goal. So this page is actually almost identical to what was shown in a previous talk. So we describe our singularity data by a metric, a two tensor, two matter field, and they have to satisfy certain constraints that we derive, and these are defined on the singularity. So there is a reference singularity manifold that we use. And if you have such an object, we're able to define an asymptotic profile, which it's pretty much the same notion as the seed data that are defined first, or the reference matrix next, and now the asymptotic profile. It's basically always the same kind of idea. Maybe even if mathematically it's different. So we are in a quiescent regime. And then I define the notion of scattering map by just saying it's a map that satisfies certain coordinate invariant and locality property. So anything reasonable, allowing you to jump from the singularity data one side to the other side. This is what I call a singularity map. And if I have that, of course, I can define spacetimes by connecting, using my map. Whenever I need to connect, I use this map. Okay, so there's not too much to say about that. There is a notion of S-cyclic spacetime based on this. And we have a local theory which consists just by applying the results of Luc Foner-Davlos, for instance, or Igor Onionsky and collaborators. So we apply these techniques and we can just glue this gluing. But the main point is not there for us. The main point is what gluing is allowed. And this is, if I have maybe 2 to 3 more minutes, maybe I can show this to you. So our classification starts with conditions that you impose. First you impose, to make things practical, you impose certain conditions on your map. So the only assumption that we impose in the end of the analysis is the so-called ultra-local property. So the way I define the junction is local, say ultra-local. So at a point after the bounds, I have state values that I define from values before the bounds at the same point. Okay. And so based on only starting with that, you can then make various classification of saying maybe the two metrics will be connected by the conformal factor or by something we call rigidly conformal factor, momentum preserving, momentum reversing, idempotent, invertible. It's just some sub-classifications that we also introduce. But in the end of the day, handling that and looking at these conditions, so really solve. We look at the constraints on the singularity. We don't assume any symmetry, otherwise we would not get what I'm giving you now. No symmetry. And what we do is that we construct solutions to the constraint in order to impose, to deduce, I would say, to probe maybe the properties of the scattering maps. So what I'm showing you in the last screen, last 1 or 2 screens, are the results of doing this analysis. And this is what you get if you assume rigidly conformal maps, even though I didn't tell you exactly what it means, but basically the two metrics are conformally related. Then you get the classifications that there are only 2 classes of junctions that are possible. And then we have a second theorem below that's a general classification. We don't put this restriction, and we again get the same results, that there are only two possibilities, two classes. And the two classes are called, isotropic bands or non-isotropic bands. And if you look at the formula in red, in the first case, you will just transform the metric before and after by a conformal factor. And this conformal factor will be a scalar function of the data, of the matter content before, and the determinant of K. And in the second case, it will be basically, something in the same spirit with a single scalar valued function. So it's really amazing that the junction, you could think that maybe this junction could be done almost randomly, and you could put anything and still have some consistency with the Einstein equations, but that's not the case. If you want some consistency, you have only a scalar valued parameter that you can choose, or actually not choose, but recover from some higher order physics. And in fact, we can state, and I will stop with this. So we can state our results in the form of certain laws that are satisfied at the singularity. So this screen is actually equivalent to the screen before, and they somehow classify, they order the information in three laws that say how K transform, or how the matter transform, and how this the metric transform. And there are very few parameters. There are basically one or two scalar valued functions that you need to pick it. So thank you. I think I should stop with this. I hope I was not too long.